We're starting in a minute or so.
Presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Good morning, everybody. I hope you're having a beautiful day out and welcome you on to today's live lecture. So, if it's your first time here, my name is Dan. Formerly I'm Dr. Page, but you just call me Dan or Daniel. Hope you're having an amazing day so far. I want to welcome you on down here and hope you're excited to learn some more computer science. So, Before I get into today's lecture, which will be on exploring properties of regular languages, I have a couple quick things to mention. Oh, thank you for the good morning wishes. Let me get the chat open. So one remark I need to always make is that if the chat is visible on the screen, if you're, say, for example, on Twitch, it will be audible to the stream, but be aware that when the chat isn't visible, I still can see the chat. It is right here. In addition, I can hear it with my earpiece. So just keep in mind, just because you don't see the chat doesn't mean I don't see or can't respond to it. Just please keep that in mind. Because if you have any questions while we're exploring these topics, or you have anything fun to say, please, I encourage it. Just don't be too edgy in the chat, okay? Just not too edgy. Just anything that's it's okay enough. But I just need to make sure I mention that. So I usually go in between each part of our lecture, each kind of major part of the lecture. I usually stop in between just for a brief break. If anybody needs to ask me any, I would argue, more meaty questions, or they want to see an example, please let me know. But if you have questions while we're doing things, please put it in the chat. If it's something I can quickly address, I'll just address it on the spot. Otherwise, I'll just wait for just a few minutes. Once I get to the next intermission, I'll address it. If it's something I can't address on the fly, as in, it will just massively disrupt where we're going with things. And I must stress that the lecture isn't just me here, right? It's actually a part of all of what we're doing here together. So any lecture I give on a topic might change depending on how the audience is. If an audience has great questions or they have anything they want to contribute, usually it helps spice up the lecture even further. So usually the more people we have coming and joining the fun or listening in, it makes the lecture better, I would argue. So if you have questions, things like that, or if you have comments, you're not sure about anything, please just let me know and I can help. It helps make the lecture a little bit more lively than it would be otherwise. Because the lecture is not just what I do here, it is what all of us do. So other than this, just a couple quick other things. First, if you haven't filled out our survey for availability, we're trying to calibrate our live programming. So if you have not responded to the survey yet, it's available on the social media pages for Page Wizard Games Learning Entertainment. Depending on where you're watching this, if you're watching this, for example, on YouTube, it's in the description. Actually, let me go quickly get the survey, and I'll put it in the Twitch chat. Let me just get that. I had it just sitting there, let's throw it in here. It doesn't really hurt.
https://forums.gle/m1gsrbimhqmg94
Accessa indeed. Accessa indeed. Anyways, we've gotten some responses. So far, it's looking like people are more available in the evenings, and they much prefer that way. And I've got some interesting topics I've been told about. So, for example, I've had some suggestions for things like randomized algorithms, Turing machines, context-free languages. Context-free languages is going to be one of the next major things we're going to be exploring in this Theory of Computation series. So that's great. That's great. But I am very compelled to explore some more of these topics. In addition, I am planning to go through some more series that have been recommended by my supporters on Patreon. If you're not a supporter yet, please consider being a supporter at patreon.com/pagewizard. It helps keep the lights on. In addition, it helps me continue to do what I'm doing as an academic, whether it be research, which I am still doing. I do pretty much almost every other day. We actually just had a paper accepted the other day for a conference, which I was very excited about. This is great work I did with another professor, and of course with one of his PhD students. It's wonderful stuff. Hello, Miss Kitty. How you doing? How you doing? You having a good day? Hello. You gonna say hi to everybody up here? You're so goofy. Such a goofy kitty. Yeah.
Kit KST.
Cat. The Kit Kat. The Kit Kat. Are you a Kit Kat? She's just ignoring that. She just does not want to take in the Kit Kat. Hey, Miss Kitty. Give me back my hand, okay? Miss Kitty's having a blast, but Miss Kitty, you're gonna go lay down for somewhere else for just a little bit, okay? Okay, my little friend, you're very excited. Yeah, I know, you love being on camera. Hey, come on. Yeah, man, you get to go on a little... As Miss Kitty's disrupting the lecture. There we go. Let me just, I'm just gonna fix the feed there. Let me just, there we go. My apologies. You know, it's a weird graphical glitch today. If you probably did, I did as well. So anyways, Miss Kitty, whenever she shows up, sort of causes a lot of chaos on the stream. So she might be back later, I'm not sure. Depends on a lot of things. So back to what I was saying. I was talking about Patreon. So please consider supporting on patreon.com/pagewizard. After this lecture, so later today, I'll be posting today's lecture notes. So if you're wondering what the notes are that I have in front of me, these will be available to all those interested in learning computer science for my supporters at the supporter access tier or higher. So please consider supporting affordable computer science education. In addition, consider supporting academics outside of universities. Another thing I wanted to mention is if you had not had a chance to check out my video on academic freedom that I released on Sunday, please consider checking that out. It's just about 2 minutes long. I would like to get your feedback or comments, and of course, please share it with your friends. I consider this a rather important issue in Canada. Like, that's where we are. So please consider sharing it with your friends, because I think more people need to be aware that there are concerns about academic freedom in Canada. And there's all sorts of other academic issues within Canada's universities. So I will be talking about more of these things in the future. So if you do like to hear more about that kind of stuff as well, consider supporting as well. Because, like I said, I am trying to operate independently. And that allows me to address topics that would not be otherwise easily discussable at a university at the current time. Because universities are rather hostile to the concept of academic freedom in these days. Which is rather unfortunate, because academics need to be able to be academics to do their job. And unfortunately, many academics are not doing their job. It's just like when, say for example, you get a firefighter. You expect the firefighter, when they get a call for an emergency, that they go put out the fire as soon as possible, right? Well, imagine if you had a firefighter that just decided, I don't know, I don't really want to put out that person's fire because of X, Y, and Z. You'd think that would violate the principles of their occupation, right? The same issue here. In fact, I would argue it's probably, if it didn't involve people's lives, it'd probably be arguably far more fundamental, because this is about people that pursue truth claims and knowledge creation. But anyways, I think that's everything I gotta really touch upon before we get started. Is everybody excited about today's lecture? So I'll give you a flavor for what we're gonna be doing here today. So in previous lectures, we talked a lot about regular languages. In fact, the last month, with the exception of our cryptography lecture, we've just been talking about regular languages. Also, some of last month as well. So this lecture actually should be, with the exception of maybe one or two other topics I may present in the future, may cap off the discussion we have about regular languages. There may be some more, however, that I might come back to, because they're interesting topics in their own right, both from a theoretical and practical standpoint. So today's lecture, I would arguably call this, like, if there's such a thing as like a theoretical coleslaw, like where you take a whole bunch of ingredients and you chop them together and you throw them together into a slaw, like a coleslaw. This is basically that lecture. So I'm going to be taking and talking about different properties that regular languages have that we have not discussed before. And so surprisingly, how you could come up with reasons for why that is the case, and show some basic instructions for how you might go about it. Some of them are surprisingly simple in the case of regular languages. In addition, we will be considering and testing properties that regular languages have. For example, we're going to address the ultimate question we're going to address in today's lecture is the question of, if I give you two languages, suppose they're both regular, is there a way I could test if this language is in fact equal to this other language? Now you might ask, Dan, how the heck do you do that? Well, they both have, like, how do you do that? Well, we're going to talk about that. That's going to be actually the final thing we'll talk about here today. We'll also see some other things such as testing if a language is empty or not, which will actually be a key ingredient for proving a claim like that. So that's actually something we will be doing. So we'll be seeing we'll talk a little bit about algorithms today. We'll also talk about some properties that regular languages have in relation to automata. So anyways, why don't we get started? So today we're going to be talking about more properties of regular languages. Namely, we're going to explore a series of different results pertaining to regular languages that we have not discussed yet in our previous lectures. So the first one I was going to be talking about is going to involve taking the complement of a language. That's pretty much every string that isn't in the language that you're interested in. But prior to this, I just have a few remarks just to revisit or emphasize them. So the first thing I want to mention, so let's talk about some more properties. So these are just going to be quicker because we've already actually talked a little bit about this already. More properties of regular languages. Oh, this marker's a little kooky. I'm gonna switch for a different one shortly. More properties of regular expressions. That O's a little bit funny. Let me give it a little bit more of a shape to it. It needs to be more rotund, right? So, a few things. I thought this would be a good way of us to get started because we've actually talked a little bit about this before. Let's talk about this. And I'm going to pose them more as questions before we get to our topic mainly here today. So, is any finite language regular? So that's our first question I want to ask you. Is any finite language regular? What does the chat think about this? What does everybody think about this? So if I give you a finite language, so it means that you could actually label of them. This is actually, the answer is yes. You might ask, Dan, why is that the case? Well, I just want to give you a hypothetical case here, just to give you an example. So imagine I had a list of these strings that are in the language. I'm just going to give them names. So like L1, L2, L3, and so on, L to some LF, where F it might represent the count of how many there are in that language. Well, if you notice that this is actually just a finite number of strings, right? Meaning that you really just have to have, so for example, if you think about this in terms of automata, you would just design the DFA such that it accepts on these strings. So you can imagine almost like you have just a whole bunch of pathways. But I must stress that you would have this as an epsilon NFA. So you would give the option to transition to any one of the pathways, just akin to what we did when we were detecting keywords. You might do something like that. You can also think about this in terms of regular expressions too. So, for example, one way you could go about this is you would imagine that you could have, okay, this one, or this one, or this one. You imagine it as a bunch of ors. So I could take L1 or L2 or L3 or up to LF, right? So I encourage you to think about what the regular expression would look like. It's really not too scary. So in this case, the answer is yes. So, how about this? So we define regular operators as union. We also had star, right? And we also had concatenation, right? So, or in a regular expression, we wrote this as plus, we had star, and we also had concatenation. Either way, they're the same things, mainly. Just one's in discussion about regular expressions, one is a regular operator. So, our regular operators actually, I'll say this way. So another question, just sort of remind us where we are regular languages closed under regular operators? So here's another question. Are regular languages closed under regular operators? So for those that aren't familiar with the phrase closed, so imagine I give you a regular language. Like this. Like suppose I call it L1. So that's the name of the language. I just call it's a variable that I've just assigned it. So suppose that this is a regular language. Suppose I apply the star operator to it. Is the resulting language still regular? Just likewise in the same vein, it could be the case that I give you two regular languages and I say, okay, L2 union L1. And if say these are both regular languages, is it still a regular language when I perform one of these operations? That's what I mean by closed. It preserves the property. In this case, that it's regular. So is the answer yes or no? We've talked about this before. I just want to bring it up because it's going to be relevant for us here today. So any thoughts? Any thoughts about this one? So all we have to do, so remember, because these are the three we're interested in. So union, star, concatenation. Usually I'd put concatenation here, but whatever. They're three. So is it closed under regular operators? So if I give you a regular language and perhaps another regular language, if I perform one of these regular operators on one of them or both of them, will it still be regular? Well, the answer is yes. There's a couple of ways you could derive this. The first one is depending on how you define a regular language. So we always define the regular language as pertaining to the existence of a deterministic finite automaton, right? A DFA. Well, using Kleini's theorem, we've shown the equivalency between the existence of a DFA and the existence of a regular expression that describes the same language, right? Do you notice that I could describe things just like this using regular operators in the context of regular expressions, right? So you can take any one of these, you can construct an epsilon NFA, which can be transformed or converted over to being a DFA. So the mere ability to do this by writing them out as regular expressions is a way you can obtain another regular expression, right? This regular expression, by definition, is like this is a regular expression by definition, right? But we've established that for any one of these, there is a DFA, right? So, of course, the answer is yes. So, if you're wondering about the proofs for these, you could pretty much argue it the same way I just stated. Another interesting thing I should also disclose to you is in the past we actually explored something called Thompson's construction. And we've seen how to take a regular expression. Sorry, Thompson's. For some reason, I'm being silly. Thompson's construction. So we actually previously explored Thompson's construction when we came up with the part of Kleini's theorem that establishes that for any regular expression, there's a way to construct an equivalent epsilon NFA. So we came up with Thompson's construction. You might recall from the way the construction works, we talked about what you do with a union, we do with concatenation and star. This actually also gives you a key ingredient if I ever gave you epsilon NFAs or DFAs and I wanted to build an epsilon NFA that describes the equivalent language. So if you recall back there, I gave you actually like 3 standard constructions, and usually people remember these constructions. If you use that as the building block to create new epsilon NFAs from pre-existing DFAs or epsilon NFAs or NFAs, you can use these constructions for each one of these respective operators to actually build automata for the equivalent language that would be the result of the operation. So I'll let you think about that. And so if you're wondering, okay, so how can I build a DFA or an epsilon NFA? Well, specifically an epsilon NFA in this case, you could just use the constructions from Thompson's construction, those cases that we had, to build them. So I'll let you go back to that lecture and you can take a look at that if you're curious. So the main thing I really want to get to is, so I must stress that once you have the epsilon FA, you can make it into a DFA using the subset construction, right? So today we're going to be exploring different properties beyond these ones. We've actually already talked about these ones. So what we're going to do first is I want to address different operators that we can do. So the first thing I thought we would start off with is suppose L is regular. Suppose I give you a language L and it's regular. We're going to consider the complement of L. So I'm going to denote this as L bar. So you might ask, Dan, what is the complement of a language? Well, imagine I imagine I have my strings in my language, right? What the complement is that you take all possible strings, you take away the ones that belong to the language in question. It's everything that isn't in the original language, but doesn't include what's in the original language. Is that clear? So just think about it like this. So imagine I give you, so here's my language. Everything outside of the language is outside this circle, right? So what I need to do is the complement would simply be all of the strings that don't belong to that language. So that's what the complement of a language is. So what I want to do for you is I'm going to show you how if you take the complement of a regular language, you still end up with a regular language. So we're going to prove this here together. So naturally, the strategy here is going to be that, okay, so imagine I have a language L. What by definition, that means that there exists a DFA that recognizes that language. I'm going to show you how to build another DFA using this DFA and show that there's actually a property that this new DFA has in relation to the original one. It's going to be surprisingly simple. It might be the first thing you might think about trying to do. And we'll see an example of how you use this. So that's the game plan. So by definition, there exists a DFA M. So I'm going to give it a name. I'll call it M. Q sigma delta Q0 F. You might recognize this 5 tuple from the definition that recognizes L, which is going to, of course, be equal to the language of M. Right? So now I'm going to show you how you take and create another DFA. So consider M bar. I'm just going to call it M bar. That's its name. I could have called it Bob for all I care. It's just a name. It's going to be Q sigma. So it's going to have the same 5 tuple with one change. And you might ask, okay, so Dan, what's going to be different here? It's going to be that we're going to make the set of final states be something that will feel a little bit natural to what I just described up here. So you recall that the set of final states, when a DFA reads an input string, it makes transitions by reading symbol by symbol, right? And it accepts if the DFA is in one of the states that's a final state, right? Well, what I am proposing to you is that you should be able to just simply consider this new set of final states to be every state but the original final states. So we'll see an example after the proof. So that's what this says. This is Q set minus F. So I'm just taking the set of states. I'm removing the final states from it. So it's just going to be everything that isn't one of the final states. So it's every non-final state becomes a final state. And all the final states of the original DFA are now non-final. So now, observe. So think about now how the execution of a DFA works. So you read symbol by symbol, the input string, and it'll end up in a state, right? At the end of this. Well, let's think about what that means within the definition of acceptance of a DFA. So, observe that when M finishes, so that's the original DFA, finishes reading W, reading string W. If W is in the language L, that's what it means, is in, it accepts as it is in a final state. I'll say it like this, in a state of F, which is the set of final states. And what happens when W isn't in the language? What happens? What happens? So if it's in the language, it accepts it, right? Because it'll land up in a final state of M. Well, think about it. And whenever W isn't in the language, it rejects, right? Why? Because it won't be in one of the final states. As M is in a non-final state. So take a look now at how we constructed M bar. So notice that it accepts, in this case, because it was in one of these states here. And rejects when it's in a non-final state. Do you notice that now all I've done is I've just taken all the states that were non-final states, but now they're final states in the new DFA. So do you notice very quickly that this is going to be where it's going to flip the reasoning here, right? So notice that it's going to be now that if W is in the language, it's going to reject, right? Because now those states are now non-final, and it's going to accept whenever it's not in the language, right? But what does that mean? What does that mean? Well, think about it. If these are all the possible strings inside of this circle, or whatever this is going to be all the strings in the language, right? The DFA originally accepted all the ones in the circle. It rejects all the ones I've just shaded outside of it. So, however, now what I've done is I've just simply flipped the sucker. So now what's going to happen is it's going to now accept all the ones out here and reject all the ones inside the funny circle. So by construction, whenever W is accepted by M, W will be rejected by M bar. Similarly, any string W that isn't in the language L will be rejected by M. For what reason? What's the reason why it rejects again? Because it's in a non-final state, right? As M will be in a non-final state. In a non-final state. So this state will be a final state in M bar, right? So similarly, any string W not in the language L will be rejected by M, as M will be in a non-final state, right? So this state, so the one it would be going to, will be a final state in M bar. In M bar. But what does that mean for M bar, for that string W? What does it do? What's it going to do? It's going to accept, right? As every string not in L is in L bar, right? The complement of the language consists of all the strings not in L, right? It follows that M bar, so here's the big connection. M bar accepts a string W if and only if W is in L bar. Therefore, since I've just presented to you now a DFA that has this property, it will accept L bar. So in fact, it decides it. It recognizes the language. It means that L bar is regular. And that completes the proof. So let's see an example of how simple this little tweak can be. So let's consider an example similar to one I think I may have mentioned in the past. So I'm going to draw its transition diagram. So I'm going to give you a DFA. It's going to have two states, Q0 and Q1. Q0 and Q1, they'll stay in their respective states whenever it reads a 1. It'll flip to the other state upon reading a 0. So this is what M would be. For example, if I gave you a given DFA. So notice that Q0 is the final state. So what should happen then if I wanted to make this DFA recognize whatever this DFA would reject, meaning that it's the complement, right? So what would I do to this DFA? What change do I need to make based on what we just discussed here? So while you're thinking about that, I'll remind you what this DFA will recognize. So notice that this DFA so notice it stays in Q0. If, say, for example, you read no zeros, it stays in Q0, right? Because it'll just read ones, right? Or it'll just be finished reading the input. Whenever it reads a 0, it goes to Q1. Then reads another 0, it goes back to Q0. Do you notice that there has to be a property of how many times 0 appears in the string, right? For example, if I give you a string that looks like this, like 0, 0, 0, 1, notice that it'll go Q0 to Q1, Q1 to back to Q0, and then it will go Q0, Q1, and then it reads the 1, stays in Q1. It would reject this string. So what property does this, like what kind of strings does this DFA accept then? It accepts strings with an even number of zeros. So any binary string with an even number of zeros, this DFA will accept it. That's what it recognizes. It recognizes all binary strings with an even number of zeros, right? So let's see what happens. So you know that if I wanted to get every other string, you know it's going to actually have to be these ones, for example, ones with an odd number of zeros. So if you have that intuition in mind, you'll notice that this is going to feel very natural for this example, but you'll notice I'm not going to be specifically tailoring it to this example. It's just to help you see how I could tweak with it. So if I wanted to get my M prime in the proof, all I do is I take all of the what used to be final states, I'm going to make them non-final, and I'm going to assign all the other states of the original DFA to be final states. So in this case, all I'm going to do is I'm going to swap which ones of these are the final states. So in this case, Q0 is now non-final. Q1 is going to be a final state. I'm not going to touch anything else. And that's how we're going to construct a DFA that accepts the complement of language L, where L would be the language that's recognized by M. So you notice very quickly with this example that we have on the board over here, that whenever I have an odd number of zeros now, it accepts. Whenever now it has an even number, it rejects. So you could do this with any DFA. So this is a really simple little tweak you can make if ever you want to get the strings that are not a part of your language. So all the ones that are not part of the language. So please just keep in mind though, and this is very important to remember, is that the language in question here is a regular language. If it isn't regular, it may not be the case that it's actually going to result in the same kind of language. In this case, a regular language. In this certain circumstance, because it's a regular language, we've shown that the complement of that language remains regular. Pretty neat, right? So are there any questions? Any questions? So all you have to do is just, whatever isn't a final state, you make it a final state in the new DFA. Whatever was a final state before, it's not final anymore. That's how simple it is to just simply get a language that is simply the complement of your language if it's regular. So I'm going to start erasing over here. And if you have any questions, just put them in the chat, okay? It's awfully quiet. It's very quiet today. So I take it there aren't any questions about this construction. So I must stress that you can just do this. It's perfectly fine. Pretty nifty. So it means that you could add complement to the operators that we have that remain closed under their operation. So, like, you know how I talked about the regular operators that we defined? You can add complement in there too, if you wanted to. it's still going to be closed. That's the big thing we really got here. So you might ask, Dan, so for those that are in tune or understand a little bit about set theory, there's a bunch of different operations that exist for sets. We actually addressed one of them, complement. So, like I said, there's always this little bit of things that happen between sets and languages. There's sort of an interesting thing that happens. So a question quite natural is if we consider other types of languages, such as those that result from a union, we know that they will still remain regular because we talked about this just a moment ago, right? That if you perform a union operation of two regular languages, it'll still end up being a regular language. There's another operation that we could do with a set called an intersection. So if I give you two languages, it would be the result of an intersection operation will be, in fact, all of the strings in that language, in this case, all the ones that belong to both sets. So you can think of union like or, and you can think of intersection like and. So if you imagine you take the strings in each one of the languages, you say, okay, it's either this one, it's this one or this one. Don't include the word either. That's something else. We have a string in one language or the other one. That's why we kind of lump them all into one big bucket, right? That's what a union operation would do. Intersection, you would imagine I give you this string and this string. If they're both there, then you include it in the set. If they're not both present in the set, or language in this case, then we would just discard it. So that's the intuitive way of thinking about intersection. Think of it like and. Both have to be present in the sets to be included in the resulting set of an intersection operation. So it's denoted with, union is like a big fancy U, like a wide U. Intersection is a wide cap. So it's like an upside down wide U. Some people refer to it as a cap. So we're going to talk about this next. So previously we had talked about complement, and we showed actually that if you give me a regular language, that the result of the complement of that language also is regular. We showed a way to transform a DFA to get a new DFA that will accept the complement of that regular language. This way, we're going to talk about another operation we could do with a set or language. We're going to talk about intersection. So suppose I give you two regular languages, L1 and L2. So L1 intersect, or intersection L2, is regular. So that's what we're actually be proving here. So just as a reminder, so suppose I have one language, and suppose I have another language. Keep in mind, it doesn't have to look like this. So all the strings in L1 are right here. All the strings in L2 are right here. Here's a Venn diagram. So where would the strings, as a result of an intersection, appear? I'm going to put numbers for these different regions of the Venn diagram. So if I were to perform an intersection operation of L1 and L2, what strings would I get as a result? Would they appear in region 1, region 2, region 3, or some combination of these? So think of union like or. Intersection is natural to think of like and, because its definition says, hey, look, if the string, in our case, if we're talking about languages, if our string is present in both L1 and L2, then most certainly you'll be in the result of the intersection. So you can see quite quickly, once you immediately see this, that it'll be region number 2. So that's what the strings will get as a result of an intersection operation. So if I perform an intersection, the claim here is that I'm going to show you now, and it's actually surprisingly simple if you remember anything about set theory. So I'm going to give a set theoretic proof for this. So it's going to use properties of sets. So that if I do an intersection, it still remains regular. So I'm going to use something called De Morgan's law. Now, if you've studied sets before, you'll be familiar probably with De Morgan's law. But I will just invoke it. Why? Because here's the game plan. I would like to make this so it looks like union. If I can make it look like union, and I can express it in terms of things I know if I apply that operation, the result would be still a regular language, then I'm okay, right? And fortunate for us, we've already actually just shown that the complement of a regular language is still regular. So as long as it remains in the terms of unions and complements, we're okay. So that's why I'm going to use De Morgan's law, because De Morgan's law gives us something that will be just like that. If you just remember, these are just, a language is just a set, right? It's just a kind of set. So by De Morgan's law, L1 intersect L2 is equal to the following. It's L1, L2. What's going to happen with these? Well, what's going to happen is I can write this out equivalently as the complements of L1 and L2. That's the first thing I'm going to need. And I end up with a union. But I must stress that I also have to take the complement of this. So I have the complement of L1, the complement of L2. I perform a union of that, which as I'm going to explain in a moment, this remains regular, right? But if I take the complement of that, which is a regular language, then it still is regular from our previous argument, right? This gives us the key ingredient. Since L1 and L2 are regular, L1 bar and L2 bar are also regular. So I'm just going to mention that we proved this before. So you would invoke this. This is the thing you would invoke. So the union of two regular languages is still regular, right? The union of two regular languages is regular. So L1 bar union L2 bar is regular. So notice I'm just really just saying what I'm just writing down what I said earlier. Finally, the complement of a regular language is regular. Therefore, L1 bar union L2 bar, where I take the complement of all of this at the end, which of course equals L1 intersect L2, is regular. And that completes the proof. Surprisingly simple. So all I really needed here was first that we established that the complement of a regular language is still regular, and we used De Morgan's law. Because we already knew prior to this as well that the union of two regular languages is still regular, right? And that's it. That's it. It's surprisingly simple. So I was thinking, I'm going to try to knock out another one here. This one's also surprisingly simple. Let's talk about set difference. We've actually talked about set minus or set difference actually already. So we're going to use a very similar strategy for proving that this language right here that I'm going to get as a result of performing a set difference is going to still be regular. So suppose I give you two regular languages, L1 and L2. L1 set difference or set minus L2 is regular. Now I'm going to use this as a building block. So this is going to be a building block from the previous proof, okay? Because I can actually express, this is going to be the kicker. You know how I built upon other closure properties that I had before? I'm going to do the same thing here, but use intersection now, seeing as I've established it for intersection. So it's going to be even easier, because if you know how to convert set difference into a statement about intersection, then you're done for the most part. So given any two regular languages, L1 set minus L2 is of course going to be equal to L1 intersect L2 bar. So I'll let you check that. If you think back to your Venn diagram over here, it makes a lot of sense. So you notice it's just L1 where I take away everything that's L2, right? So this is one way I can model taking away. So I have L1, I take everything that's in common with the things that are not in L2. So since the complement of any regular language is regular, so is L2 bar. Therefore, now I'm just going to invoke what I just proved over there. Therefore, since intersection is closed for regular languages, L1 intersect L2 bar, which is of course equal to L1 set minus L2, is regular. And that's it. That's the proof. Pretty nifty, right? So notice that the strategy when I was trying to going about with these proofs is I picked up my other properties like they were tools, and I expressed them in set theoretic terms, the things that I already knew how to express as regular languages. So the way I got this proof to work was quite simple, right? I got it to express it in terms of things I already knew if I apply those operations would yield a regular language. So that's the whole trick I did. It's the same thing over there. Just that one it looked a little crafty because I had used Morgan's law. So this just establishes that we have more closure properties with more set theoretic operations. So, are there any questions? Any questions at all? So, we had intersection, we also got these. So, you might look at this right away and say, Dan, that's pretty nifty. That means that regular languages actually have a lot of nice properties in the sense that there's a lot of things you can express with them, but as we've already established, not every language is regular. We've seen that by using the pumping lemma previously. So it's not like an ultimate thing, right? You can't just simply say, yeah, I could build any language out of these things. And the unfortunate thing is you can't. Because there's going to be some languages that are simply not regular. All of these require that the languages are regular in the first place, right? So you can only build regular things out of other regular things. Is that clear? There's going to be some fun cases where you take a more sophisticated language and you end up with a regular language. But that's something we'd see much, much later once we explore things like context-free languages. So in those, you can actually show that if you do specific things to a context-free language, you end up with a regular language. which is fascinating. So let me just erase the board here. If you have any questions, please put them in the chat. But the big message here is that all these standard operations, they don't get you anywhere new than just, I'm still stuck in regular land, okay? That's another way you can think about this. The positive, more utilitarian way of viewing this is that, hey, look, all these operations, I can use these to craft regular expressions or automata, and I can still end up with them, right? Or I know for sure when I do them, when I perform these operations, I still end up with something that is what I expect it to be, right? But the catch, of course, is that, sure, you can use it for designing things, but you still stay in the land of regular languages. You don't get anything beyond what we currently have. That's the other side of the coin. So there's a positive way of looking at it, very utilitarian way. There's a negative way of looking at it, meaning that we don't get anything more versatile out of doing things like this. As in, things that just can't be described by a DFA. So, if there aren't any questions, let's get to our next property I would like to explore. The next one's going to be a little bit fun, because we've never talked about reversal yet. Reversal is another thing we can do with a string. A string, we can always take a string, and we can always reverse it, right? What if I wanted to talk about the language that is simply consisting of all of the strings that are the same ones, but in reverse? I think that's a fun thing to consider. So we're going to consider that, and I'm going to show you how you can take like an automaton and come up with one that will accept on the reversal of it. Surprisingly simple. So I'm not going to get too overly formal about it. So previously we had talked actually about some more closure properties. I thought I would show us a different operation we could do or consider for a language or a string respectively. Is called reversal. We haven't talked about reversal yet. So let me define it. The reversal of a string W, be A1, A2, suppose these are the symbols, just giving them names. So it's A1, A2, AN minus 1, AN, all the way up to N. So it's N symbols. Is the string written backwards. So, i.e., it would just be AN minus 1 down to A2, A1. So let's do a concrete example, just make sure I'm clarifying myself carefully here. If I give you the word kitty, can somebody tell me what the reversal of kitty is? What's the reversal of kitty? So if I give you kitty, this string here, what's the reversal of kitty? Well, it is Y-T-T-I-K, right? You just take the same string, you write it backwards. So I'm going to denote this reversal like an operation of sorts. We will denote the reversal of a string. String W as W with a capital R in the exponent position. Likewise, denote, so if I have a language now, I could go through each one of the strings You can imagine I could go through each one of the strings and I give the reversal of that string. I can talk about the reverse of a language. Denote the reverse of a language. Reverse of a language, L, as L with the capital R in the exponent. So here's what I'm going to show you today is I'm going to show you how you can obtain the following property. So if L is regular, this is the claim. If L is regular, so is L reversal. So I'm going to give you a sketch of the proof because I think it's simple enough to play around with. So I'll encourage you to pick up a DFA, an epsilon. Actually, in this case, we're going to consider an epsilon NFA. We're going to consider an epsilon NFA if you were to go formally prove this, okay? Because if it's regular, then most certainly there exists an epsilon NFA. The epsilon NFA makes this much easier to go about this, at least as far as I'm concerned. So to prove the claim, there are a couple different ways. So I'm just going to sketch one out for you. There are a couple different ways. So I don't claim this is like the only way you can go about it. That difference look a little odd there. This says different here. It's a little different, right? You get it? You get it? The different ways. Below is a sketch of one. Okay. So I'm going to walk through a sketch of how you'd prove this. So one, you already know that if L is regular, then there is an epsilon NFA, M, that recognizes L, right? We know this. It's by Kleini's theorem. So namely, we use the subset construction to obtain an equivalent D of A, right? But also note Kleini's theorem also gets us back around. So if ever we need to go the other direction, we can always cut our way through with a regular expression, if need be. But we already established that subset construction does exactly what we need. Let's say that recognizes L. So we're going to construct a new epsilon NFA from this epsilon NFA. Construct a new epsilon NFA, M prime, that recognizes LR or L reversal as follows. Now you might ask, Dan, what are you going to do now? What are we going to do? Well, it's going to feel very natural for the operation, right? So you can imagine you have your start state, right? To get from the start state to a final state, you follow a sequence of transitions which are directed edges, right? Or arcs. So a very natural graph theoretic way of thinking about this process is you're exploring the graph by navigating a directed path or directed walk, right? Well, you follow the arrows, right? Well, if I wanted to do this, but in reverse, what do I do with those directed edges then? What do I do with them? I reverse them, right? So that's the first thing I'm going to do. Reverse all the arcs. Reverse all the arcs for transitions of M in M prime. Now, we have to do something about the start state and the final state, right? Make the final state in M prime the start state of M, right? It has to get to the start state. That's where it begins in M. So if we need this new epsilon FA to work properly, I just want to make sure it gets over there. But you might ask, Dan, why do you want to use an epsilon FA? There's one issue that we have not addressed yet. Think about it. Here's just a little doodle. So imagine I have the start state. Imagine there's just some states here that the transitions occur on or something like that. And suppose that some of these are final states, right? Some are final states. Who knows? There could be self loops in here. But say a couple of these are final states. Well, in this construction, it says to reverse all of these, right? You're supposed to reverse all of the arcs. And then you assign the final state in the new epsilon FA to be the start state, right? But here's a bit of a problem, right? There might be multiple final states. So what do I do with these multiple final states then? They surely all can't be a start state, right? You only can have one of those. So what do I do? Well, we're going to do something that is very natural if you think about this in terms of graphs. So if you have multiple final states, well, why don't we try to pretend that all of these final states are actually just one start state? And one way I can do this is by creating a new state that is the new start state of this epsilon FA that I'm building. But I make it so that I can use epsilon transitions so I could freely get to the old final states of the original epsilon FA. So in effect, I am pretending that many final states are actually just one start state. And it's all because of the epsilon move that I'm allowed to take. So create a new start state Q0 prime in M prime, where it transitions on epsilon. It's important that it's epsilon to all the accepting or final states of M. So the accepting states of M. So in M prime, you would just use those what those final states would have been. And now those are going to have epsilon moves towards them, completing the construction. Now, here's the other key observation is, you might ask, Dan, well, okay, so what can you do? What can we say about this new epsilon FA M prime? Well, here's the other part of the proof. So once you got this, so M prime simulates in reverse. So I'm going to put that in quotation marks. It's a little small here. It says M prime simulates in reverse M, meaning that M accepts W if and only if M prime accepts W reverse. So I encourage you to pick up an epsilon NFA. So take any one of the examples we played around with in the past. Then what you do is you try to use this construction and see if you end up with exactly what we claimed here. I encourage you to try writing this out more formally, but these are all the key ingredients for the proof. So, that being said, if you go through this carefully, make sure you convince yourself that it is in fact correct. If I give you a regular language L, then its reversal is also regular. So are there any questions about that one? That one, I like this one. It's a lot of fun. I didn't go through a formal proof with you, as in me walking you through carefully with the full-blown arguments, but these are all the bits and pieces you would use. So you would describe this construction first, and then you would prove this. Now, you might ask, Dan, how do you prove that? Well, there's several different ways you can go about it, but you just look at the definitions, right? So you just look at what it means to accept in the new epsilon NFA versus acceptance in the old epsilon NFA. And you might be staring at this saying, Dan, why did you use epsilon NFAs and not DFAs? Like I said, we need it for this last step here. So I create a new start state using the epsilon moves. If you don't like that it's an epsilon NFA, remember, when you're done with this epsilon NFA, you can always turn it into an NFA or a DFA. So if you don't like it that has epsilon moves, then you could get rid of those just using the subset construction. So what we're going to be doing next is we're going to start looking at testing properties of languages. So a very common question that comes up in formal language theory is, if I give you a language and another language, is there any relationship that these two things can have? Can they, for example, are they equal to each other? If I give you a language, is it empty? How do I know that if I give you a string W, is it in the language or it isn't in the language? Now, that last one, we've already been exploring for a number of months at this stage now. But I need to make sure I pin it down, because we can still do this sort of stuff efficiently depending on how we represent or describe the language. So for example, if it's just a DFA or automaton, it's really fast to test membership. As long as if you have it built, it's just a matter of just simulating it, reading the input, see if you land up in a final state, just as an example. So this will be the last thing we'll explore here today. It might sound like we're already almost done, but we're not technically almost done yet. These steps, each of these have rather delicate steps to them, but once you understand the main idea, it's actually really nice. And at the heart of at least one of these will be actually some graph theory, which is, whenever I get my hands on some graphs, I usually get very excited. So that's one thing I can always tell you about graphs when it comes to me. If I can see that it can be modeled as a graph, I get quite excited about it. So often when people study formal languages, they often want to ask or test properties that the languages have. In this case, I want to start asking questions about regular languages. So there's many different kind of questions you can ask, but these are examples of decision problems. So the one that we could explore first, and this is the first one I'll talk about, is testing emptiness. So I want to know, is language L empty? Is it the empty set or empty language? So depending on how you represent L, it might help you answer this question. So I'm going to address this depending on how we represent the language in question. Specifically, we're going to be interested in when this language is regular. The much more general question is a little bit trickier. Actually, it's quite a bit. Being tricky is just a gross underestimation of how difficult it could be, possibly. I don't want to talk too much about that. I want to talk only about being regular. So we want to test if L is empty or not. So these are examples of decision problems. So suppose that I want to take a finite automaton. I'm not going to be overly specific on which kind. The idea should work regardless. And at the heart of this is actually going to be just simply some graph theory. So just recall, and this is true regardless if we're talking about DFA, NFA, or epsilon NFA. Recall a string W. String W is accepted by a finite automaton M if and only if what? What has to be true always if W is accepted by a finite automaton? M is in a final state upon reading W, right? It's in a final state. I was about to write a finite state. That would be a little concerning. Is in a final state. Now, if you think about this carefully, if I wanted to know if L is empty or not, this is actually be reframed as a different question. Because, for example, just let me just doodle something here off to the side for you. Just a little doodle. Suppose that there's a final state right here. Suppose I have just, say, some finite automaton. It looks something like this. I don't know. It's just an example. And I go from the start state. Do you notice that these symbol, which would be along this edge, right? So the existence of a string that gets accepted by M is actually just asking a different question, but it's actually an equivalent one. Is can I reach from this vertex in this directed graph, from this vertex, the start state, or start vertex as I could just describe it now, can I reach the final state? There's many ways I can get to this final state in this example, but if there exists no directed path or walk from the start state to the final state, what does that mean then? What does that mean? If there's no way I could get from here to there, regardless of what, like, I just don't really care about what the symbols are here, but if I can't get from here to there, in this case I can, but suppose that I couldn't. What does that mean? So if a string is accepted by the finite automaton, then M is in a final state, right? So if no string is accepted by the finite automaton, then M isn't in a final state, right? That means that anywhere I go isn't this one or any other final state, right? So testing emptiness is testing whether the final state, or I'll say a final state, not the, because there could be several of these, right? A final state is reachable. Now, the minute you hear this phrase, if you've taken any course on graph algorithms or just analysis of algorithms, if you've explored graphs before in some capacity involving exploring graphs, this phrase should just stick out to you like a sore thumb. Reachable from the start state. So this is actually a graph reachability question. It's actually asking if there exists a directed path or walk from the start state to any one final state, right? That is, we can carry out a process as follows. So you imagine I have an initial starting place for how I would define what reachable means. The start state is reachable from the start state, right? Then, now if I want to inductively define what reachable means, here's how I would do that inductively. If state Q is reachable, from the start state, and there is an arc or transition, whatever terminology you would like to use, an arc or transition from Q to P on any input symbol or epsilon, of course. I'm just going to throw that in parentheses here because it might be an epsilon NFA. Then P is reachable. So what does that mean now? You might actually look at this for a moment and say, Dan, didn't we see something kind of like this actually before? We did actually in a much more restrictive capacity. When we defined the concept of an epsilon closure, we defined the idea that there's a set of states that are reachable via epsilon transitions or moves, right? So if you actually look at this definition of reachable, which is reachable from the start state, this should remind you a lot of it, except what we're doing is we're not going to care about what the input symbols are. We're just going to look at what the directed edges or arcs or transitions are. I don't care about what the symbols are. I'm just going to look at the underlying structure of the transition diagram, which is a directed graph, right? So now all you have to do is compute all states. We're just going to compute all states reachable from the start state. So now all you do is when you're done computing this, which again, it should remind you a lot of how we define an epsilon closure, except we're ignoring this restriction that it has to be on an epsilon move. It could be any symbols or epsilon. So any input symbols or epsilon. We just disregard those. We just care about what are the directed edges doing or transitions. So you end up with a set of states when you apply this definition, when you want to try to compute all of them. So at the end of this, I end up with a set of states or vertices, and all I have to do is examine if any one of them belongs to the set of final states. If state Q is in the set of final states, it's in the final states, so it's among one of them. What does that mean? Based on what we discussed. That the answer is no, right? There exists a directed walk, which corresponds to reading off symbols that get me from the start state to the final state, right? So for example, if I were to apply this definition, and I said I want to compute all the reachable states, you'll notice that every one of these states will actually be included in that set. So I examine each one of those. One of them's the final state, and I would conclude that the language described by this DFA, or whatever finite automaton it is, it definitely isn't empty, because there exists a directed walk that takes me from the start state to one of the final states. In this case, there's just one, right? So now it's really a question of, are the set of reachable states, if none of them are a final state, then you can conclude what? Well, remember how we defined acceptance, right? Well, there has to be no way to get to a final state. So, I'm going to use a semicolon. Some slick stuff here. I'm going to use a semicolon. Otherwise, every state reachable from the start state, is non-accepting or non-final. And return yes. That's it. So that's how you could go about testing whether a language is empty or not using a finite automaton. So if I describe the language using a finite automaton, you'd use this graph theoretic approach for testing emptiness. So if you're asking, Dan, how do I implement this reachable process? Well, you could use depth first search or breadth first search, for example. Those two, if you know what those are, you could just adapt those, because you could use this concept of reachability or reachable within that context, because a graph traversal algorithm will be able to compute the set of vertices that are visited by the algorithm. And those visited are the states reachable from whatever vertex or state you'd like to start from. In this case, you just pick the start state always, as opposed to an arbitrary vertex or state. Okay. Now, another way we could describe a regular language is with a regular expression. You might ask, Dan, how can I test the emptiness whether there's no strings that regular expression describes? Well, I have some good news and bad news. The good news is, yeah, you could certainly do it this way. But the bad news is that you're going to have to transform it so you can do this. If you want to do it really, a simple way of doing this is just that's one of my bad news, is that a simple way of doing this is just to use what we just talked about. I don't claim there's other ways of doing it, but most certainly that's one of the simplest ways of doing it. So you just convert the regular expression to an epsilon NFA and do the above. Right? Because Kleini's theorem, we've seen how we can do that. We use Thompson's construction to do it. But yeah, so this is how we could test whether a language that's regular is empty or not. So are there any questions? Any questions? Any questions about that one? So it's all really just a question about exploring a graph. Darn it, I should have worn my hat. I have my hat here. I should have worn my hat because we were going exploring. Missed opportunity. Poop. So let me erase the board. If there's any questions, just let me know. There's a lot of things we can ask as forms of decision questions or decision problems.
SMH.
I know, it's absolutely disgraceful that I forgot about the hat. You know, whenever I go exploring, I wear the hat. That's the way it is. Whether I go to the beach, whether I go venture in the jungle.
Hat tax.
We don't question the hat religion, okay? For I have sinned. I have blasphemed against the graph traversal gods. AKA the hat tax. It's the hat tax. How much percent do I lose now? What's the percent of the hat tax? What's the percent for the hat tax? I'm not sure.
40%.
40%? Who does it go to? Who does this 40% go to? And I don't even know what I'm paying in. Am I paying in cat food or something? Or am I paying in dinosaurs? What am I paying in, and who's getting this hat tax?
Government regulated LOL.
Oh, poop. They always come up with new ways to get you. It's awful. But anyways, when we get to our next couple things we would like to test, I'm going to do them both together, given that the first one is really easy for me to walk through because we've actually talked about it many times. The other one is actually the more interesting one, and it actually will be the last property I'll talk about in today's lecture. So we're going to talk about testing the membership. So if I give you a string, I want to know if it's in the language or not, which we've talked about for at least a couple months now, right? Like, if I give you a string, I want to know if it's in the language or not in the language. We framed this whole discussion about decision problems actually within this question. So if I want to know if a string's in the language or not, we talked about it as accepting or not accepting of the DFA, right? Say, for example, when we're talking about regular languages. So I'm going to talk about that first, and then I'm going to talk about if I give you two languages, how do I know that they're equal or not? So if somebody proposes to you, just to give you an idea of the implications of this, if somebody describes to you a regular language, they may have a DFA for it, and somebody else may have another language, which they may describe with an epsilon NFA or a regular expression. And I want to know, is the person giving me the DFA and the person that are giving me the regular expression, are they actually describing the exact same set of strings? So that's what we're going to be talking about. And I'm going to show you which it'll take some more work on the end of somebody thinking about the things we talked about previously, but I'll show you how to do it using set theoretic operations. But if you think about what we talked about earlier, how I talked about Thompson's construction, and how you could take parts of the DFAs or epsilon NFAs and build them up in specific ways, you most certainly can use the construction that's in this proof. I'm just going to describe it in set theoretic terms. I haven't really given you general templates for intersection and set difference, I believe. If there's interest in that at some point, I might consider actually walking through these constructions one more time. But I haven't talked about those two. But not as common when it comes to talking about this, because they're not really a part of Thompson's construction, at least the standard proof for it. But let's get into this. So previously we had talked about how we can test if a language is empty or not. In addition, we've also talked about a bunch of closure properties. For example, we talked about the regular operators. We also talked about intersection, complement, and also reversal. So I'm going to now talk about two more kinds of properties you might test. One is going to be very common for us. We've talked about this many times. We've framed decision problems like this, is testing membership. So if I want to know if a string is in a language or not, this is actually how we introduced the idea of thinking about a language as a decision problem. And this is one way you might think about this. So given a string W, is W in the language? Very, very interesting question. So let's address this for regular languages. So suppose that L is regular. So we're going to talk about it in this context. We've talked about this many times, so I'm going to go a little fast on this. But I'm going to talk more about complexity, namely, and the process. So suppose that L was described by a finite automaton. So what you do is you would simulate, or just run it, right? You simulate the finite automaton. Processing string W. So processing W. So if the automaton ends in a final state, what does that mean? It means it accepts, right? Which means it's a part of the language, which you would return yes, right? Otherwise, it's no, right? Otherwise, you read this, the automaton read W and now is in a non-final state, right? So otherwise, answer no. Okay. Now, suppose that the length of the string was n. When the length of W is equal to n, and a DFA is represented, I'm going to stress that the main ideas here are going to be generally true for finite automata, but other kinds as well. But I'm just going to restrict this just to DFA. And a DFA is represented as a two-dimensional array, which is, of course, its transition table, which we talked way back. This is one natural way to implement a DFA in terms of how you represent it as a transition table. Each transition takes constant time, and the test overall takes big O of n time, where n, of course, is the length of the input. So this is quite natural, right? Because we read each symbol one after the other, right? And so we transition to another state, but notice that the execution is completely dependent on the length of the string. Now, you might ask, okay, suppose it's a regular expression instead. Now, this is just one way of going about it. It's going to be very similar to what I said previously. So you can always convert the regular expression to a finite automaton. Such as an epsilon FA using Thompson's construction to a finite automaton. Then perform the above. So remember, this discussion applies to just any finite automaton. Just I wanted to keep it simple for us. Now, this was a piece of cake, right? We've talked about this for many lectures. We've talked about everything has always been in the context of testing if something's in a language or not in terms of the strings, right? Well, let's ask a different question. And you might ask, Dan, why should I care about this? Well, let's think about this. I'm just waiting for the phone to stop ringing. in case it's doing anything funny. We're just waiting for it. There, I think it stopped. Okay, so we're gonna consider our last property. We're gonna consider here is if we are given two regular languages suppose we call them L1 and L2. How do we test if L1 is equal to L2? Now you might be looking at this saying, Dan, why should I care about if I give you two regular languages? How do I know that they're equal or not? Well, think about it this way. You have two people, person A, person B. Person A comes up with a DFA. Person B comes up with a regular expression. And I would like to know, is person A's DFA is going to be describing the same language as person B's regular expression? Once you see it like that, now it's more of a question of are we actually seeing that these things are in fact, are they actually the same language that we're describing? So if somebody posits to different ways of representing one of these regular languages, are we missing any strings, or in fact it's actually the exact same language we're talking about? So that's the motivation. That's one of the main motivations here. So I'm going to present this as a theorem. So here's a theorem. So I'm going to use some set theoretic fun here to go about this. So I'll let you think about the steps of this proof. But I must assure you, the way I'm going to present it to you is going to use set theoretic operations. So I just warn you that that the way this proof is going to play out is more about the existence of a DFA as opposed to me showing you how to build the DFA. But it'll be implicit in how I define it, okay? And that part I'll let you think about. So given two languages, L1 and L2, there exists an algorithm to determine whether or not L1 is equal to L2. So let's prove this. Now, I'm going to come up with a rather, I would argue, is a little bit of a, at first it's going to look a little strange, but I'm going to design a new language that will be regular, and it's going to have a very nice property to it that we can use, and it'll actually come back to the question about determining if a language is empty or not. So by the way I'm going to come up with the language, I'm going to allow it so that it becomes really a test if the language that I come up with is empty or not. If it's empty or not, it'll tell us if they're equal or not, i.e. L1, L2. So consider, so at first it's going to come out, it's going to look a little strange at first, but if you think about it from a set theoretic standpoint, it's not too terribly scary looking. So imagine I have L1 and L2. So I'm going to consider L3. So I'm going to build L3 out of the following operations, which we all know will yield a regular language. So we're going to consider L1 intersect L2 bar union L1 bar intersect L2. Now, we're going to see why I picked L3 like this. I got a little excited there. So, since L3 is regular, and I'll leave this as an exercise for you to prove using the similar kind of arguments we've seen when we built expressions like this, using set operations. Since L3 is regular, there exists a DFA. There exists a DFA that recognizes L3. Right? Now, you might ask, Dan, what's the algorithm going to look like? Well, I'm going to come up with this DFA, right? So I have the DFA. Then I'm going to now test for emptiness on L3. Now, if you're looking very carefully at this, you might notice that I'm actually describing something that looks like set difference. So I'll get to that in a moment. So check whether L3 is empty or not. Using the reachability process described previously. What you could actually show is that L3 is empty, it's the empty language, if and only if L1 is equal to L2. So now what I want to do is I want to convince you that this is in fact the case, so I'm going to make an argument showing you that this two-directional connection here is existent. So I'm going to prove both directions separately. So let's watch this carefully. So I'm going to actually prove them over here, just for the sake of brevity, that I don't want to cram everything on over here. So this is, at first you're going to, so I really want you to take note of L3 over there. So I'm going to show you that I can rewrite parts of L3 in a really nice, simple way that should expose very quickly why I picked L3 like this in the proof. It's actually that we're secretly crafting a test for emptiness. And the test of emptiness requires that L1 is equal to L2 for it to be empty. So let's prove this claim. Let's prove the part that says if L3 is empty, then L1 is equal to L2. So we're going to prove that part first. So if L3 is in fact empty, then what does that mean by definition? Then it has to be that both, because remember, it's connected by a union, right? So we have the first part and the second part, then there's a union in between, right? So that means that then both L1 intersect L2 complement, which this, if you look carefully at this, is actually just set difference. This has to be equal to the empty set. But what does that mean? Well, this is another way of me saying that L1 is actually a subset of L2. Why? Well, think about it. That means that for this to be empty means that I was able to take out everything using L2. Meaning that L1 has to have at least whatever's in L2 to do that. That's at least one part of this. Both this and L1 bar intersect L2, which if you look at this carefully, this is another way of me writing the following. It's just really L2, because remember, I could just go like that. It's L2 set minus L1 is empty, which this implies that L2 is a subset of L1 are true. So both of these have to be true. Actually, let me get rid of the both, because that's just too much. There's too much both in this proof. It's true. So, what does that mean then? So for those that are acquainted with sets, I've just said to you, if it's empty, then L1 is a subset of L2. But that also means that that L2 is a subset of L1. That means everything that would have been in L1 has to be within at least L2, and everything in L2 is at least within L1. But what does that mean? They're equal, by definition. That's what set equality means. So that's what it means for two sets to be equal. By the definition of set equality, L1 is equal to L2. So if L3 is empty, then L1 is equal to L2. Now let's prove the other direction. So this direction is saying if L1 is equal to L2, then L3 has to be empty. So if L1 is equal to L2, then, now this one's going to be, I like this part of the proof, it's fun. Then L3 is equal to L1 intersect L2 complement union L1 complement intersect L2, right? But what does it say? If L1 is equal to L2, what happens here and what happens here? So if they're equal to each other, well, L1 is L2, right? So that means that if I may as well just put L1 right here. But that's L1 complement. What happens then? So let's look at the picture here. So imagine I have L1, and L1 is equal to L2. So L1 is equal to L2. That's a circle right here. Out here, outside of this, that's L1 complement. And remember, intersection means take the elements that are in common, right? Are there any elements in common among L1 and the complement of L1? No, there's none, right? All of these are out here. All of these are within here. But there's none in common. So this is the empty set. So it's the empty set or empty language union. By the same reasoning, you could say the same thing here. Which this is equal to the empty set. It's empty set or empty language union empty language. It's just an empty language, completing the proof. Thus, I've come up with a way to test if L1 and L2, given that they're regular, that there exists an algorithm for testing equality of two languages. And at the heart of this algorithm is constructing this emptiness detecting language that is also regular, and I apply the reachability process to it that we've already seen when we were testing emptiness of a language. So we've seen how we could do that. Pretty nifty, right? So notice how everything sort of stacks on top of each other. In this case, we use actually numerous things. So for example, that step where I showed you that L3 is so I just said it was regular. That's actually a key part that used everything that we talked about with some of these other properties we've seen about regular languages. So it all comes together nicely, isn't that's pretty neat, right? Miss Kitty, what do you think of that? Miss Kitty, what do you think of that? She thought it was pretty neat. Okay, Miss Kitty. Are there any last questions before, because that's all I got for today when it comes to talking about properties of regular languages. So, presuming anything else, I might talk about a little bit more about regular languages. If not, this is pretty much a nice way of capping off regular languages, at least for now. And we'll talk maybe more about other formal languages in the future. So, are there any last questions before we go for today? So I just want to remind you while you're thinking about a question, if you have any questions, Remember that these notes will be available on patreon.com/pagewizard or at Subscribestar. Just check the links. They will be available there later today. They're available at the supporter access tier, which is only $5 a month, which is insane in the context of learning at an advanced level like this. So keep that in mind. It's insane in a good way, just to be very clear. It's crazy. It's crazy. It's a good time. But I hope you consider joining the fun. If say, for example, you missed last time or you're joining this first time, thank you for coming on by. Please consider subscribing and telling your friends to come join the fun. The more people that are here for our lecture, the better it tends to go when it comes to asking questions. Especially, it's great for a review. Say if you're a student taking a computer science program and you're wanting to enhance your learning or boost your learning, this is an excellent way to do so. So consider supporting at patreon.com/pagewizard. There's all sorts of rewards. I am covering all sorts of topics, especially related to theoretical computer science, which often serves one of the major backbones of any good computer science program. So data structures, algorithms, theory of computation, algorithms. We're talking about all that good stuff here. I know I said it twice. That's how important it is. So, with that being said, please consider supporting, and thank you so much. And even just telling your friends, just give it a thumbs up, give a follow. Those little things do matter a lot to me, and especially to the work that I do here. So, please consider supporting, and I'll see you later this week with some more Chrono Trigger. Hopefully we won't have as many stream disruptions like we had last time. I don't know what the heck happened there. I don't know what happened. So I'll say thank you so much, everybody, and have yourself a beautiful day. I'll see you later.